Hello. In this video, I'm going to be going through this problem here. I'll first read this out. 3 points are located at the vertices of an equilateral triangle whose side equals A. They all start moving simultaneously with velocity v constant in modulus, with the first point heading continually for the second for the third, and the third for the first. How soon will the points converge? Okay, so the question is asking how soon will the points meet at a single point or collide. So the question tells us that these 3 points are located at the vertices of an equilateral triangle. So I'll first draw this equilateral triangle. And we know that the 3 points are located at the vertices. So here is point 1, here is point 2, and here is point 3. And the question tells us that the side length of the triangle is equal to A. And we know that each point on the triangle moves with a constant velocity v, so the velocity v is constant in modulus. So if I say that the velocity of point 1 is equal to v1, the vector v1, and the velocity of point 2 is equal to v2, and the velocity of point 3 is equal to v3, I can write that v1, the magnitude of v1, is equal to the magnitude of v2, which is equal to the magnitude of v3, and these 3 are all equal to the velocity v, which is given in the question. And if I draw on these vectors on the diagram, so point 1 is moving with v1, so it is aiming towards point 2, and point 2 is moving with velocity v2, aiming towards point 3, and 3 is moving with velocity v3, aiming to point 1. And as we know that the magnitudes of v1, v2 and v3 equal v, they are the same, and the 3 points, they are equal distances away because they are separated by the side length of the equilateral triangle. We can see that from symmetry, these 3 points are going to meet in the centre of this equilateral triangle because everything is the same for them. They are equal distances away and they are all travelling the same velocity modulus v, so they are going to meet in the centre of the triangle. So I can draw point 1's path, so it's going to look like this, and point 2's path will look like this, and point 3's path will look like this, and they will meet in the centre of this equilateral triangle. Now this is from the frame of reference of a stationary observer. So this is what a stationary observer would see. So for example this observer here. And to solve this question, we already know what the velocity of each of these points is, it's v, and the question is asking us to work out how soon the points will converge. So all we really need is the distance each point travels. However, we can see from the diagram that each point's path is a curve, and so it makes it quite difficult to calculate this distance. However, this question is made easier if we think from the frame of reference of one of these points. For example, point 1. So let's say we have an observer who is placed on top of point 1. And if an observer was on point 1, what they would see is point 2 moving towards it with a certain velocity. And in order to work out this relative velocity, we can draw a diagram. So initially at t equals 0, so v2 was initially in this direction, and here is point 2, so point 2 was initially there, and initially v1 was in this direction. And here is point 1. Point 1 and point 2. And because we want to work out the relative velocity of point 2 with respect to point 1, we need to take a component of point 2's velocity, v2, in the direction of v1. So the way we can do this is, if I move this vector v1 here, so I'll just move the vector, I can now take a component of v2 in the direction of v1. So we know what the angle between v1 and v2 is, so this angle theta. We know what the value of theta is because this is an equilateral triangle, and so this angle here is equal to pi minus theta. And therefore the component of the vector v2 in the direction of v1, the component of that is equal to the magnitude of v2, which we know is equal to v cos the angle in between v2 and v1, pi minus theta. And we know that cos pi minus theta is equal to minus cos theta, so this is equal to minus v cos theta. Now, this is the component of v2 in the direction of v1, so it is this component. But if we want to work out the relative velocity, so the velocity of particle 2 with respect to particle 1, we have to subtract particle 1's own velocity, so the magnitude of v1. So the relative velocity of point 2 with respect to point 1 is equal to, so if I call that VR, that is equal to the velocity of particle 2 in the direction of v1, so minus v cos theta, minus point 1's own velocity, so the magnitude of v1, which is equal to v. So minus v cos theta minus v. And simplifying this, we get minus v times cos theta plus 1. And because we know that this is an equilateral triangle, as you can see here, it's an equilateral triangle, therefore the value of theta is 60 degrees. So this equals to VR equals to cos 60 is equal to a half, so this equals minus 3v over 2. So this is the relative velocity of point 2 from the frame of reference of point 1. So this is the velocity that point 1 would see point 2 moving towards it with. Now we also know that when we are in the frame of reference of point 1 can see that the distance between itself and point 2 is going to be decreasing. So if we say that the distance between point 1 and point 2 is x, just the variable x, we know that a unit change in x, the distance between point 1 and 2, over a unit change in time, so we can write dx dt, we know that this is equal to the relative velocity of point 2 with respect to point 1, which we just worked out, so it's equal to this VR. So dx dt equals VR. So if we rearrange this, we get dx equals VR dt. And now we can integrate this. So on the left hand side, for dx, we know that the initial distance between points 1 and 2, so the initial value of x, was equal to a, because points 1 and 2 are separated by one side of the equilateral triangle, so a distance of a. And we also know that when points 1 and 2 collide, when they converge in the centre of the equilateral triangle, the distance between them is 0. So it will be from a to 0. And on the right hand side, it will be from when t equals 0, from when time equals 0 to some unknown time, capital T, which is the time it takes for the points to converge. And this time, capital T, this is the same time that is measured by both observers. So the stationary observer and the observer on point 1, they would measure the same time. So T, capital T, is the same for both of them, and that's why this method works. Even though we are in the frame of reference of point 1. Capital T is the same for both observers. Okay, so now if we substitute in the value of VR, which was 3v minus 3v over 2, minus 3v over 2. So we have integration dx h0 equals and minus 3v over 2 is a constant, so it can be taken out of the integration. So we get minus a equals minus 3vt over 2. So a equals 3vt over 2. And if we rearrange it to get the value of capital T, we get t equals 2a over 3v. And that's the final answer. So the question asks us for the time taken for the points to converge, and our capital T is equal to 2a over 3v.